So in this unit of force vectors, what I'm going to be discussing today is Cartesian vectors and the addition of Cartesian vectors. So what we have here. So for a vector A, and when I denote a vector, I'll put the arrow above it. So for vector A with a magnitude of A, then the unit vector U sub A will be defined as such. Going forward, characteristics of a unit vector. The characteristics are as such. The unit vector is, or I should say has, a magnitude of 1. Unit vector is dimensionless, and a unit vector points in the same direction as the original vector A. The unit vectors in the Cartesian axes system are I, j, and k. So they're the unit vectors along the positive x, y, and z axes respectively. So let's consider this box that I've drawn with sides a sub x, a sub y, and a sub z. And they're a sub x, a sub y, a sub z, we'll say meters long. So the vector A can be defined as a sub x I plus a sub y j plus a sub z k. All right. So then the projection of vector A, right? The projection of vector A, as you can see in that xy plane, is A prime, and I labeled it A prime in light blue. So we could find the magnitude of A prime by using the same approach as a 2D vector, right? So we could use that same approach and we could say A sub x squared plus A sub y squared to the 1/2 power. If you recall our approach when dealing with 2D vectors, it was this same approach. So then the magnitude of the position vector A, that magnitude of the position vector A can now be obtained as we'll have A prime squared plus A sub z squared, right? That's raised to the 1/2 power. So this is equal to A sub x squared plus A sub y squared plus A sub z squared, and again raised to the 1/2 power. So the direction or orientation of vector A is going to be defined by the angles alpha, beta, and gamma. So let me input those into the diagram where we can see it. So alpha here to here, right? And then beta is going to be from here to here. And then gamma there to there. So as you can see, these angles are measured between the vector and the positive x, y, and z axes respectively. So their range of values are from 0 degrees to 180 degrees. And then using trigonometry, direction cosines are found by using cosine of alpha is a sub x over a, cosine of beta, a sub y over a, and then cosine of gamma is a sub z over a. So these angles are not independent, right? They're not independent. They have to satisfy the following equation: cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. So this result, we can actually derive it from the definition of a coordinate, direction, angles, and the unit vector. All right, so if you recall the formula for finding the unit vector of any position vector, u sub a, vector a over a, which is going to give us a sub x over a I plus a sub y over a j plus a sub c over a k direction. Or written another way, it can be u sub a is equal to cosine alpha I plus cosine beta j plus cosine gamma k. All right, so once individual vectors are written in Cartesian form, it's going to be easy to add or subtract them. The process is basically the same as when 2D vectors are added, right? When we have f sub r, sum of the f's, it's going to be sum of f, let's see, sub x I plus the sum f sub y j plus the sum f sub z k. So, for example, if a, right, is equal to, say, a sub x I plus a sub y j plus a sub z k, and b is going to be b sub x I plus b sub y j plus b sub z k, then from this we can do, okay, a plus b is going to be ax plus b sub x, a sub x plus b sub x, the i's, plus a sub y plus b sub y j plus a sub z plus b sub z, and this will be k. All right, or we could also show a minus b. So then I'll just write a sub x minus b sub x I plus a sub, a sub x minus b sub x. I'm sorry, I'm writing x's again. I should be writing j's. Should be writing y's. This is j direction plus a sub z. It's a minus. Remember, That's minus b sub z k. And then sometimes 3D vector information, sometimes it's given as magnitude and the coordinate direction angles. Magnitude and coordinate direction angles. Or the magnitude and the projection angles. So you should be able to use both these sets of information to change the representation of the vector into the Cartesian form, right? i.e., say it was like 10I minus 20J plus 30K or something like that. Let's begin with an example. So let's say we're given the diagram to the right that we have two forces. We'll call them F sub 1 and F sub 2 as noted in the diagram. So these two forces are actually applied to a hook. So what do we need to do? So we're here to find the resultant force, and we're going to do this in the Cartesian vector form. So we're going to find the resultant force in the Cartesian vector form. So our plan, and it's good to plan things out when working through these problems, is to use using geometry and trigonometry. We're going to write F sub 1 and F sub 2 in Cartesian vector form, and then after that we're going to add the two forces by adding the x and y components, right? So let's first resolve this force right here, F sub 1. So if we take F sub x equaling 0, so this is going to be 0 pounds. And if we take F sub y, which we do have information on here using the triangle, 3, 4, 5 triangle that's given, we have 500, right? And we multiply it times 4 over 5. So that's the adjacent over the hypotenuse, because we're looking at that y, right? So you do that calculation, crunch those numbers in your calculator, you get 400 pounds. And then we can look at F sub z, and that's going to be 500. And for the z, according to the diagram, we can go with, what's that, for the z-axis, the opposite over the hypotenuse, so that'll be 3 over 5, right? And then crunch those numbers in your calculator, you should get 300 pounds. All right, so the next thing we can do is now write F sub 1 in our Cartesian vector form, right? Don't forget the units. So that's going to be 0I plus what we have as 400J plus 300K, and this was all in pounds. All right, so then we're going to resolve the next one, which is F sub 2. Resolve F sub 2. Okay, so I brought up another diagram to make it a little bit more clear what we're doing in this next step. So now we're going to resolve force F sub 2. So if we have F sub 2, I'm sorry, 2z, So that's going to look like negative 800 times the sine of 45 degrees. All right, so that looks like it's negative 565.7 pounds. And then we have f sub 2 prime. If you recall our explanation earlier when we had that, if you go back into the lecture, we had the a, but then a prime was its projection in that x and y axis. So this is a similar type of thinking, right? We're finding we can see that the f prime here is going to be 800 cosine 45, which is 565.7 pounds. So f sub 2 prime, we can further resolve it as f sub 2x and f sub 2y. So f sub 2x is going to be for us 565.7 cosine 30, and sub y is 565.7 sine 30. All right, so let's crunch those numbers and see what we get. I get 489.9 and 282.8 pounds. All right, so thus we can write f sub 2 is going to be 489.9 I, right, the x direction, plus 282.8 J minus 565.7 K. And we said this is in pounds. Okay, so, and that takes us to saying that f sub r, that resultant, is just going to equal f sub 1 plus f sub 2. So f sub 1 is our 0I plus 400J plus 300K pounds. And f sub 2 is the 489I plus 282.8J, and I'm sorry, it's 489.9I plus 282.8J minus 565.7K pounds, so that's 489.9. All right, so then we can say f sub r, the resultant for us is going to be it's 4, let's see, we can just say 489.9, you can say 490 I plus 683J minus, that's about 266K pounds.